Now, to start our Year 12 unit on trigonometry, let's just think about some things that we learnt last time we looked at trig. We learnt about radians, and the reason that we learnt about them is so that we could get some scale to our graphs that would make sense, so that now, when we use calculus with our trig curves, the gradients of the curves are actually meaningful. Because when we first learnt how to graph something like y equals sine x, we learnt that it does one full rotation every 360 degrees. But we also saw that when we're looking at gradients of curves, the actual gradient really matters. And when we differentiate a curve, what we're finding is the gradient there. So if we have this scale whereby this graph goes up and down from 1 to -1 on the y-axis, but it has gradations of 360 the other way, clearly the scales are very different on each axis. But what we also saw is that if we use radians as our measure for angles, then we can say every 2 pi is our one full revolution of the curve. And now we have a scale where 1 unit on the y-axis equals 1 unit on the x-axis. And this is really important when we use our calculus because the gradient will actually be a meaningful number. So we need to always use radians when we're using calculus with trig. But something else that we're going to learn today, we're going to have a look at the behaviour of each of these curves near the origin. Now, we've already memorised the shapes of the curves, so this shouldn't be too much of a surprise, but we're going to come up with some results that help us to make approximations when x is a very, very small angle and we're finding the sine, the cos, or the tan of x. Now, we're going to start by just having a guess, taking an educated guess about the behaviour of each of these things and having a look at what we already know, because that educated guess is going to give us a really good understanding, and in fact already, if we just look at this concept, it should make sense. Then I'll show you a proof, which you don't need to write down, but you can just watch, listen, understand, so that you can see where these exact identities come from. So if we're looking at what happens when they're near the origin, well, we've got the sine curve always begins at 0, goes up and down like this. The cos curve is just like a shifting along or a translation of the sine curve, also does a full rotation every 2 pi. And we have a period of only pi for the tan curve, and you'll notice that like the sine curve, it goes through the origin. So if we take just these two and now zoom in to what's happening right here at the origin, we get something like this. And if I draw in the line y equals x, which we know has a gradient of 1, we see something really interesting, which is that both of these curves actually coincide with that line as they go through the origin. And this kind of makes sense. If we think about how we're used to drawing these, they do seem like they head off at a gradient of 1, don't they? And it turns out that they do. Now we're learning this first before we see the proof for it. But I think it makes a lot of sense because we've been drawing them like this already, even though we didn't really know the gradient there. So it makes sense that the sine curve, which is coming through like this, is going to be above that line y equals x when it's this side of the origin. But on the right-hand side of the origin, it's going to dip and curve away from that line y equals x. Whereas y equals tan x will do the opposite. It'll duck down underneath the line y equals x on this side of the origin, but on this side it will come up above it. Now, if we can have this picture in our mind, this is an important one to write down. You probably don't need these because you've got them elsewhere in your book. But let's start with a quick sketch of this. So if I was to say what is the behaviour of sine x and tan x when it's near the origin, it'd be really sensible to say, well, they behave a lot like the line y equals x. In other words, there's a gradient of 1 there. Now, what do we know about a gradient of 1? Well, every rise of 1 coincides with a run of 1. So we get these little right-angled triangles, if you like, that are just as wide as they are tall in and around that area. Now remember that we're zoomed right in here, so we're looking at very small values of x, and we can see that whatever x is, y would be much the same, wouldn't it? Now our other case, if we zoom in here and have a look at what cos x will be close to as x gets really, really small and we get closer and closer to a value of x being 0, well, when x is 0, cos of x is exactly 1, isn't it? So when x is almost 0, just a very, very tiny number, a really small angle, cos of x is going to be pretty close to 1, isn't it? Now we just considered the gradient of the sine curve and the tan curve when they're very close to the origin, and we found that that gradient is actually 1. Now we haven't had a proof for it yet, but let's just hold that in our minds so we can see what we can do with this piece of information. Now gradient is rise over run. So if I've graphed the sine curve, then I can call this x and y and x, or I could actually call this the sine of x, because that's what I'm graphing on the y-axis. And so my rise over run down here, the rise will be the sine of x, and the run will just be x. So what we're saying here is as we get closer and closer to x being 0, the rise over the run is going to approach 1. And similarly with the tan curve, as x gets closer and closer to 0, the rise over the run of that curve is going to approach 1. So looking at just these two first, because we've worked that out using the gradients there, we can consider what that means. Just multiplying both sides of the equation by x, we can see that as x approaches 0, sine x and x are going to be very close to the same thing, because when you divide one by the other, you get 1. Now, we've used different terminology here. This one takes a limit as x approaches 0, but it says what that limit equals. Obviously, it won't get to that unless x actually is 0, and yet we can't divide by 0. Here we've used different terminology and said it's approximately equal to. So two different ways of writing the same thing. And these should both make sense because we've built them from our knowledge of the gradient of those curves. Now with the cos curve, we've done something different. I haven't considered the gradient there. The gradient of the cos curve when x is 0 is actually 0. Now I haven't built a gradient of 0 here. What I've come up with is just a statement of, well, if this is the y-axis, then when I'm graphing the cos curve, I could also label it cos of x. And I can just consider as x gets really, really small and closer to 0, the cos of x gets closer and closer to 1. So the limit equals 1. Now, this is important. None of these statements make sense or are true unless x is very, very small. So this is just not just a general thing, oh, the cos of x is approximately equal to 1. No, it's only approximately equal to 1 when x is very, very small. Now, how small, you might ask? Well, for approximations that allow you to use these equations, if you like, you need x to be as small as possible. Generally, anything under 5 degrees, these will be very close to each other. And the smaller x is, the closer they'll get. So we'll have a look at that in a few examples. Now, you've taken my word for it that sine x and tan x have a gradient of 1 as they cross the origin here. We'll prove that later. But let's also have a look at another proof that proves these identities. Now, in our proof, you'll see one that looks a little bit different than this. But if I know that the cos of x is very close to 1 when x is small, it also makes sense that 1 over the cos of x will also be very close to 1. Why is that? Well, if cos of x is really cos of x over 1, if I take the reciprocal of that, I flip it upside down, if it's close to 1, 1's reciprocal is itself. So these two statements are kind of interchangeable. Once you understand one, you can reason that the other must also be true.